lovely video that I'm making for you. This video will deal with transformations. Um, and we'll be spending a couple days on this because it tends to be challenging. Um, I have a data set. This is one of the examples in your textbook where X is going to be a representative age. It's actually the midpoint of a range of ages, and Y will be the average marathon finish time. And the first thing you'll have to do is to create a scatter plot for this data set. So let's go look. I have that entered into, I believe, list 1 and list 2. So we want to look at our stat plot. I want a scatter plot. I don't think that's all the data. When I look at the data, I see that it looks curved. So that it's clearly not going to be able to use linear regression. But that particular curve looks like a quadratic to me. It's like a parabola. So what I usually do when it looks that clearly parabolic is I go to Stat, Calc, and instead of my regular linear regression, I'm going to look at number 5, quadratic equation. Quadratic regression. I want list 1, list 2. And when I do that and I calculate, it gives me a quadratic equation, y equals ax squared plus bx plus c, with the values of a, b, c, and my r squared, which tells me if I switch over to a quadratic regression analysis, I'll have 92% of my variation is going to be explained by the least squares line, but not a least squares line, a quadratic line. That's pretty good. When I do that, go back here, back to our slideshow. So I want it in the form a plus b1x plus b2x. It'll look like that, where my x, that's squared, would be age, and my y hat would be the average marathon finish time for that age. I'd like to use the specific equation. It minimizes those residuals and the sum of the squares of those residuals. These are the residuals shown on that line. You can see they're pretty small. When I graph them, I don't see a particular pattern. They're kind of randomly spread all over. I hope you're enjoying the rain as much as I am. And the calculator gave you r squared, and that again says that the 92.1% of the variation is explained by that quadratic relationship. That's pretty good. Depending on your data set, you've got cubic regression, and your calculator can calculate those regression models. Another method is to actually transform the data to make it linear, and then using the least squares regression line and fit the transformed data. And what I have here is a pomegranate study. They were injecting cancer cells in mice and finding the average tumor volume. And I'm going to show you using Fathom what the data looks like and how to transform it. Here's that data. Here's the graph of that data. If I were to find the residuals, which I can do pretty quickly on Fathom, and graph my days, oh my lord, if I graph days versus residuals, I see the very thing that I told you to look for, and that's a pattern. I see that curved pattern. that tells me it's not particularly appropriate to use a linear regression model. Um, so there's our residual plot. Now, what the text looks to do, and you can put a copy of this right on your cheat sheet, is to use kind of a ladder of transformations. So when I look at my original graph, the shape of that, when I look over at that diagram, matches shape number 2. But that tells me what I would suggest is either my x goes up the ladder from 1, the original value, so perhaps squaring my original value, or y could go down, where I could take a square root, a cube root, a logarithm, or a reciprocal. And we're going to try out a couple of these and kind of see how it looks. So I'm going back to my data. The easiest thing, I love taking a logarithm. I'm going to take the logarithm of my y, the average days. And I'm going to edit the formula. It's going to be a log. It's average tumor volume. Oops. Let's use that. And let's see how that looks on a graph. Take my days, and now that looks a lot straighter than the original data, taking the log of volume. What if I took the square root of volume? Pull another graph down here. Square root of volume. Those both look pretty good. I could take the original one and go up that ladder, so square the days. And that would be days. And we'll square it. Say okay. And let's pull down another graph. We'll have the square of our days. And we'll put in average tumor size. And again, that's another one that looks pretty straight. I'm still seeing a little bumpiness, but it looks way more linear than that original. But let's take a look at the residuals. I don't think I really like that square of the days. So we'll call them resid, square, days, formula, and this is a statistical function. Square days versus average tumor volume. And I want to look at a graph of that. And that's a little more scattered. I still have a bit of curviness to it, but it's definitely much more linear than the original. So I would probably, and none of these are going to be bad to choose, but I would probably go with the square of the days. So your text ended up looking at the log of the tumor volume versus the number of days, and they liked how linear that looked. That particular equation would then be transformed into the log of my y, which is the average tumor volume, equals 1.226 plus 0.041 times the number of days. The thing that I'm going to ask you to do is to use your transform data to make predictions. And how would I predict the average tumor size 30 days after injection of cancer cells? I want to replace my x with 30. I solve for the log of y. And that's not the average tumor size. And if I look at my original data, 30 days having a tumor size of 2.46 just doesn't make sense. I need to take the anti-log of both sides. In other words, I want to know if I take 10 to that power, what is it worth? And that would be 285.76 cubic millimeters. That latter can be used to determine what transformation would work best. So if I have a curve that looks like that one does in the upper, I could either go up for y or up for x, or both. For 2, that shape, which looks kind of exponential, I could go up for x and or down for y. I have another problem here. This one is out of the textbook as well. It's one of the section problems. I have an age and I have the average swim distance. I don't even remember for what. But I want to use my calculator to figure out, first of all, we'll look at the original data, but figure out what would be best to do. So I have that loaded, and I believe those are loaded in list 3 and list 4. And what you can't see is that I'm keeping track that list 3 has my age and list 4 has my swim distance. And my age is x and my swim distance is y. So when I look at the graph of that, I'm going to put in my x is list 3, my y is list 4. I want to look at my graph, 9. And this graph, when I look at it, has a shape that looks to be like number 1. So to resolve that, I could either go up with y and or up with x. So I'll just, if I go up from the original value, I could square one, the other, or both. So I could try first squaring age. So in list 5, I'm going to have age squared. And I'm writing that down because I won't remember some of these things afterwards. I go back to my main screen. Age is in list 3, so I say list 3, square it, store in list 5, and enter. Now, let's go look at our data. I'm going to keep my list 4 alone, but I'm changing this to list 5. And I'm going to go look. Soon 9. That looks a lot straighter. I'm wondering if squaring the swim time would make it even more straight. So I'm writing down in list 6, I'm going to square the swim that's in list 4. So list 4 squared store list 6. When I go to my stat plot, I'm going to change that to list 6. And I'm going to look at my graph. I think God, for Zoom 9. That looks really straight to me. That looks super straight to me. I'm going to use list 5 and list 6 as my transform data. So I go back out to Stat, Calc 8. I want to use list 5 and list 6. And this says that my new equation would be, if I had y equals a plus bx, I would have y hat, and I remember I squared my swim time, so it would be y hat squared equals 160,96211.9 plus my b is, it actually would be minus because my b is a negative number, minus 1,619.278 times x, or age squared. So my transformed equation would be swim distance squared equals 160,96211.9 minus 1,619.278 times the age squared. And I would be able to use that to put in an age. Good luck.